Let us begin with something simple. Imagine a flat sheet existing as a single-dimensional plane. Hold this image clearly in your mind. Now, let us make an interesting assumption. Imagine that this plane has no height at all, none, and no depth either. What would this mean for such an object? What would this strange limitation reveal about its true nature? It would mean something quite profound. It would mean that this folder exists as a one-dimensional world, a world with only a single dimension. Think about what that truly means. In this strange, flat universe, there is only one way to move, only one direction that matters, only one path that an entity could ever take. So if we imagine, just hypothetically, that some kind of organism was living inside of this one-dimensional space, what would life be like for this creature? What would its existence feel like? The answer is both simple and deeply limiting. This organism would only be able to move in a linear path. It could move forward along this single line. It could move backwards along this same line. But that would be the absolute extent of its movement. A straight line would define its entire universe. It could not turn left, it could not turn right, it could not move up or down. The concept of sideways motion would be utterly meaningless to this creature. Its entire existence would be confined to sliding back and forth along a single, straight pathway through its reality. When we really stop to contemplate this one-dimensional existence, we begin to appreciate just how constrained it would be. Consider the profound loneliness of such a world. This creature's entire universe is a line stretching in two directions. Imagine encountering another being in this space. In our three-dimensional world, if we want to pass by someone walking toward us, we simply step to the side. We move around them with barely a thought. This simple action, this casual sidestepping, would be completely impossible in a one-dimensional universe. If two one-dimensional creatures meet while traveling toward each other on their line, they face an impasse. They cannot go around each other because there is no around. There is no sideways. One must retreat, moving backward, to allow the other to pass. Or perhaps they remain stuck, unable to progress further, blocked by each other's presence. Every encounter becomes a negotiation. Every meeting is a potential barrier. The very concept of overtaking or bypassing becomes fundamentally impossible unless the obstacle chooses to move out of the way. Think about how this would affect any attempt at building a civilization or developing a society. Trade becomes extraordinarily complicated. If a creature at one end of the line wishes to deliver something to a creature at the opposite end, it must pass every single creature in between. There are no shortcuts, no alternate routes, no parallel paths, no way to go around a congested area. The structure of any one-dimensional society would necessarily be linear, probably arranged in some strict hierarchical order, because changing positions relative to one another would require elaborate coordination. Communication in such a world would face unique challenges as well. If creature A wants to send a message to creature C, but creature B sits between them on the line, the message must pass through B. There is no way to transmit information around an intermediary. Privacy becomes almost impossible. Every signal, every message, every piece of information traveling along the line must pass through all the creatures in between. Perhaps such a society would develop protocols, agreements that certain creatures would not intercept or read messages, but physically, the information must flow through them. Storage and organization would be equally problematic. Imagine trying to build a library in one dimension. You could have books arranged along the line, but to reach the book at position 100, you must physically pass by all the books at positions 1 through 99. There is no concept of shelving, no way to organize things in groups that can be accessed independently. Everything is sequential, everything is in a queue. The entire organizational structure of knowledge and resources would be fundamentally linear. And what would this creature actually perceive? We mentioned that it sees in 0 dimensions, but let us explore that strange concept more fully. 0-dimensional perception means experiencing only a single point. The creature could detect whether something is directly in front of it or not. Perhaps it senses pressure at its forward point. Perhaps it detects light or darkness at that single point of contact. Perhaps it feels temperature or texture where it touches the world, but it has absolutely no sense of distance, no perception of space extending away from it, nothing beyond immediate contact at that one point. Its world would be experienced as a sequence of discrete moments, each containing only information about whether its forward direction is blocked or open. The creature might sense blocked, 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 then suddenly open. It has passed an obstacle, but it has no way to see that obstacle approaching from a distance. It has no way to know how long the obstacle was. Everything is experienced at the single point of contact, in the immediate now, with no spatial extension to its perception. Think about how such a creature would develop concepts of distance and space. It could not see distance. It could only experience duration. If it moves forward at a constant speed and remains blocked for a long time, it learns that a large obstacle is in its path. If the blockage is brief, the obstacle was small. Distance becomes indistinguishable from time when you have no spatial perception. The creature measures everything in terms of how long it takes to traverse, not in terms of spatial extent. This has profound implications for how such a creature would understand its universe. It might not even have a concept of space as we understand it. Its entire ontology, its entire framework for understanding reality, might be built around sequences and durations rather than positions and distances. The very language such creatures would develop would reflect this. Where we might say, the obstacle is 3 meters away, they might say, the obstacle is 3 time units ahead if I move at standard speed. Now, let us move forward in our exploration. Let us step up to the 2nd dimension. When we go to the 2nd dimension, something wonderful happens. We suddenly have 2 dimensions instead of just 1. We have width stretching out in one direction, and we have length extending in another direction. These 2 dimensions create something far more interesting than a simple line. They create a plane, a flat surface where things can happen in many more ways than before. So let us think hypothetically again. If an organism lived inside of this 2-dimensional space, what would be possible for it? What kind of freedom would it have? The answer is dramatically different from our 1-dimensional creature. This 2-dimensional being would be able to move up within its flat world. It could move down, it could slide left, it could glide right, and it could move anywhere else in between these cardinal directions. It could drift diagonally, it could trace curves, it could travel in any direction across this flat surface. The freedom of movement would seem almost infinite compared to the poor 1-dimensional creature we imagined before. The expansion of possibilities is immense compared to 1 dimension. Movement becomes fluid, navigation becomes interesting. A 2-dimensional creature can maneuver around obstacles instead of being permanently blocked by them. It can explore its flat world, discovering new regions, encountering other creatures without mandatory interaction. It can choose its path, can take detours, can approach destinations from different angles. Think about how transformative this 2nd dimension is. Suddenly, parallel paths become possible. Multiple creatures can travel in the same general direction without blocking each other. They can move side by side. Trade routes can develop. Commerce can flourish without every transaction requiring passage through every intermediate point. A creature at position A can reach position C by going around position B. The entire structure of society becomes vastly more complex and flexible. But two-dimensional existence would still be strange in ways we might not immediately appreciate. Consider how this flat creature would perceive other creatures in its world. It cannot look down at them from above, because there is no above in a two-dimensional world. It can only observe them edge-on from the same flat level it occupies. It sees other creatures as lines with varying brightness and colour. Imagine you are a two-dimensional being meeting another creature in your flat world. You would see it as a line segment extending across your visual field. Maybe this line has variations in colour along its length. Maybe one end appears darker than the other because of how light falls on the curved surface of the creature's body, but you are seeing only the outline, only the edge that faces you. You cannot see the full shape of the creature. You cannot see its complete form laid out before you. You see only the slice, the one-dimensional cross-section that intersects with your line of sight. This means that a two-dimensional creature would need to move around other creatures to understand their full shape. It would need to circle around them, observing them from many different angles, piecing together a mental model of their complete outline from multiple one-dimensional snapshots. Identity and recognition would work very differently than in our world. Instead of recognizing someone by their face, by seeing their complete features all at once as we do, a two-dimensional being might recognize others by the particular sequence of brightness and color patterns they present when viewed from different angles, or perhaps by some unique marking on their edge that acts as a signature. Meeting someone for the first time in a two-dimensional world would be an elaborate process. You would circle around them, building up a complete picture of their perimeter. Are they circular, triangular, irregularly shaped? Do they have symmetry? Are there distinctive features on certain parts of their boundary? All of this information must be gathered sequentially, piece by piece, as you change your viewing angle. It would be like trying to understand what someone looks like if you could only see them through a narrow vertical slit and had to walk around them in a circle to see different parts of them through that slit. The internal structure of creatures in a two-dimensional world presents another fascinating biological puzzle. Where would their organs go? In our three-dimensional world, we have depth. Our organs are arranged inside our bodies, tucked away in the third dimension. We can have a digestive system running through the center of our body without dividing us into separate pieces. But in two dimensions, everything must be arranged in a plane. A two-dimensional creature with a digestive tract running through its body from one side to the other would be split in two. The digestive tube would divide the creature into separate parts that cannot communicate internally. The upper half and lower half would be disconnected. Unless, perhaps, the digestive tract runs along one edge of the creature's body, entering and exiting at the boundary, so the organism remains topologically connected. Or, perhaps two-dimensional life would evolve completely different solutions. Perhaps processing food through some surface absorption mechanism that does not require a through passage. The constraints of two-dimensional anatomy would force very different biological structures than we are familiar with. Consider the challenge of having a circulatory system in two dimensions. In our three-dimensional bodies, blood vessels can branch and divide, carrying nutrients to all parts of our body. Arteries and veins can run alongside each other, carrying blood in opposite directions. But in two dimensions, if a blood vessel branches, it creates separate, disconnected regions. Each region on one side of the vessel cannot communicate with regions on the other side. The organism would be fragmented by its own circulatory system. Perhaps two-dimensional life would need to be fundamentally simpler, relying on diffusion rather than active circulation. Or perhaps it would develop a radial structure with a central core and arms or lobes extending outward, each arm able to function somewhat independently. The topology of two-dimensional biology would be utterly unlike three-dimensional biology. Even seemingly simple functions like eating and excreting waste become topological puzzles when you are constrained to a plane. But here is where things become truly fascinating. A two-dimensional world has a special relationship with the dimension below it. You see, a two-dimensional world is comprised of an infinite series of one-dimensional worlds stacked upon each other. Imagine taking that single line, that one-dimensional space, and then placing another line next to it, and then another line, and another. Stack these lines infinitely close together, infinitely many of them, and suddenly you have created a flat plane. You have created a two-dimensional space from an infinite collection of one-dimensional spaces. This is not just a metaphor. This is how dimensions actually build upon each other mathematically. Each higher dimension contains an infinite number of the lower dimension arranged adjacently. The plane is made of lines. Each line is infinitesimally thin, having no width at all. But when you have infinitely many of them side by side, their collective arrangement creates width. The second dimension emerges from the infinite stacking of the first dimension. Let us think about this more carefully. When we say a line has no width, we mean it quite literally. In pure mathematics, a line is a one-dimensional object. It has length, but absolutely zero width. Zero. Not a tiny width, not a width so small we cannot measure it. Actually, zero. And yet, when we stack infinitely many of these zero-width lines side by side, we get a plane with definite width. How is this possible? How can infinite zeros sum to something positive? The answer lies in the nature of infinity. We are not adding a finite number of zeros. We are taking a limit. We imagine dividing the plane into narrower and narrower strips, each strip being essentially a line with infinitesimal width. As we take the limit where the width approaches zero and the number of strips approaches infinity, we recover the full two-dimensional plane. This is the foundation of integral calculus, summing infinitely many infinitesimal quantities to get a finite result. This same pattern continues upward. Just as the two-dimensional world is built from infinite one-dimensional lines, our three-dimensional world, which has depth and length and height, is comprised of an infinite series of two-dimensional worlds. Think about this carefully. Every slice through our three-dimensional space, every infinitely thin cross-section, is itself a two-dimensional plane. Stack these planes together, infinitely many of them, infinitely close together, and you construct the three-dimensional space we know and live in. In calculus, we use this principle constantly. When we integrate a function over a volume, we are often summing up contributions from infinitely many, infinitesimally thin slices. Each slice is essentially a two-dimensional region with an infinitesimal thickness. We calculate something about each slice and then add up all the slices to get information about the full three-dimensional volume. This mathematical technique directly reflects the way dimensions are constructed from stacks of lower dimensions. Imagine slicing a loaf of bread. Each slice is approximately two-dimensional. It has length and width but very little thickness. If you stacked all the slices back together perfectly, you would reconstruct the three-dimensional loaf. Now imagine slicing it thinner and thinner into infinitely thin slices. Each slice is a two-dimensional plane. The entire three-dimensional loaf is the sum of these infinite two-dimensional slices. This is not just an analogy, this is literally how three-dimensional space is constructed from two-dimensional planes. So now, to illustrate this concept more clearly, Imagine that I have stacked many folders upon each other, one on top of another, building upward into space. We now have 3 dimensions present in our structure. We have depth extending forward and backward, we have length stretching from side to side, and we have height reaching up and down. These 3 dimensions define our everyday reality. They describe the space we move through every single moment of our lives. Our own 3-dimensional world, the reality we inhabit, is far richer than these lower dimensional spaces. We have volume. We can contain complex structures inside our bodies. We can build buildings with multiple rooms and corridors that intersect in elaborate ways. We can create intricate machines with parts that interlock in 3 dimensions, gears within gears, nested components. We can store things inside containers hidden from view behind 3-dimensional barriers. The possibilities enabled by 3 dimensions are almost incomprehensibly greater than what would be possible in 2 dimensions. Consider the simple act of tying a knot. This requires 3 dimensions. In 2 dimensions, you cannot tie a knot in a string. If you try to cross a string over itself in 2 dimensions, the 2 parts of the string must pass through each other. They cannot go over or under. There is no over or under in a flat plane. Knots are inherently 3-dimensional structures. The entire field of knot theory, a branch of topology, exists only because we have 3 dimensions. The same is true for many other structures we take for granted. A simple chain link fence, where rings pass through other rings, is impossible in 2 dimensions. Interlocking rings require 3 dimensions to avoid intersection. Even something as simple as a door hinge, which allows rotation in a plane while maintaining a fixed axis, requires 3 dimensions to work. The mechanical possibilities of 3-dimensional space are vastly richer than 2 dimensions. But we still perceive this rich 3-dimensional world through 2-dimensional images. This is crucial to understand. Each of our eyes receives a flat image on the retina. The retina is essentially a 2-dimensional surface, covered with light-sensitive cells, rods, and cones, arranged in a curved but fundamentally 2-dimensional array. These cells detect patterns of light and dark, colors and intensities, but the information they capture is inherently 2-dimensional. It is a projection of the 3-dimensional world onto a 2-dimensional surface, not unlike how a photograph captures a 3-dimensional scene on flat film or a flat digital sensor. Our brain performs extraordinary computational work to reconstruct 3 dimensions from these 2-dimensional inputs. We have 2 eyes, and the slight difference between what each eye sees, called binocular disparity or stereoscopic vision, provides powerful information about depth. Objects that are closer appear in slightly different positions in the 2 images from our 2 eyes. Your brain compares these images, calculates the differences, and uses trigonometry, essentially, to estimate distances. The mathematics of binocular vision is actually quite elegant. If you know the distance between your 2 eyes, the baseline, and you can measure the angle at which each eye must turn to focus on an object, the convergence angle, you can calculate the distance to that object using triangulation. Your brain does this constantly, automatically, without your conscious awareness. It performs these geometric calculations millions of times per second as you scan your environment. We also use motion parallax. When we move our head from side to side, objects at different distances appear to move at different rates across our visual field. Closer objects sweep by quickly. Distant objects move more slowly. Our brain tracks these relative motions and infers the 3-dimensional layout of space from the pattern of how things move. Have you ever noticed this effect while riding in a car? Objects near the road, like fence posts and signs, zip by rapidly. More distant trees move more slowly. Mountains on the horizon barely seem to move at all. This is motion parallax. Your brain uses this information to build a depth map of the scene, estimating how far away everything is based on how quickly it moves across your visual field as you move. We use perspective. Parallel lines, like railroad tracks or the edges of a long straight road, appear to converge in the distance. Objects of known size appear smaller when farther away. Our brain knows these geometric rules, often unconsciously, and uses them to estimate distances and sizes. Artists have used perspective to create the illusion of depth on flat canvases for centuries, dating back to the Renaissance, when linear perspective was formalized. The rules of perspective are precise mathematical rules. Objects appear smaller in proportion to their distance. An object twice as far away appears half as tall. This is called the inverse square law of apparent size. Artists use vanishing points and horizon lines to ensure that parallel lines in their paintings converge properly, creating a convincing illusion of three-dimensional space on a flat surface. We use lighting and shadows extensively. When light comes from a particular direction, it creates patterns of brightness and shadow on three-dimensional surfaces. These patterns reveal the curves, the bumps, the angles of surfaces. A flat circle painted on a wall creates a very different pattern of light and shadow than a sphere protruding from the wall. Our brain is exquisitely tuned to detect these differences, having evolved to extract three-dimensional information from two-dimensional shading patterns. The study of how shading reveals shape is called shape from shading in computer vision. It is remarkably difficult to do computationally, to look at a photograph and determine what three-dimensional shape would create that particular pattern of light and shadow. Yet your brain does it effortlessly, constantly. It makes assumptions about lighting, usually that light comes from above, because that is where the sun typically is, and uses these assumptions to interpret shading as three-dimensional structure. We use occlusion. When one object blocks our view of another object, we know with certainty that the blocking object is closer. This gives us information about the relative ordering of objects in depth, even if we do not know their exact distances. If tree A partially blocks our view of tree B, then tree A must be closer to us. This is called the depth from occlusion cue. Occlusion creates layers in our perception. We mentally organize the scene into near, middle, and far layers based on what blocks what. This is why looking through a forest is so visually rich. There are dozens of layers of occlusion, trees behind trees behind trees, each slightly offset, creating a complex three-dimensional structure that our brain effortlessly parses. We use atmospheric perspective. Distant objects appear hazier, less saturated in color, with reduced contrast. This is because light scatters as it travels through the atmosphere, especially through water vapor and dust particles. On a very clear day with low humidity, this effect is minimal, and distant mountains may appear sharp. On a hazy or foggy day, it is pronounced, and objects just a few hundred meters away may appear washed out and indistinct. Our brain uses this information as another clue about distance, especially for outdoor scenes. Leonardo da Vinci was one of the first artists to systematically use atmospheric perspective in his paintings. He noticed that distant mountains appear bluish and hazy, and he replicated this effect to create depth in his landscapes. This technique became a standard tool in representational painting. We even use familiar size. If we know how big something typically is, like a car or a person, and we see it appearing small in our visual field, our brain infers that it must be far away. This can lead to illusions when our assumptions about size are wrong. If you see a miniature model car and do not realize it is a model, you might think it is a real car that is farther away than it actually is. But most of the time, this heuristic provides useful information. All of these depth cues work together simultaneously. Our brain combines them, weighs them against each other, resolves conflicts between them, and produces our seamless experience of seeing in 3 dimensions. But the fundamental visual data entering our eyes is still 2-dimensional. We have simply evolved to become very, very good at interpreting that 2-dimensional data and reconstructing the 3-dimensional world from it. This reconstruction is so good, so convincing, that we rarely realize we are not seeing 3 dimensions directly. We feel as though we perceive depth immediately, as though our eyes give us direct access to 3-dimensional space. But this is an illusion, a magnificent construction created by our brain. We are seeing a 2-dimensional projection and interpreting it as 3-dimensional space. Now, here is the question that pushes us into stranger territory. What happens if you keep going from here? What happens if we continue this pattern one more step? We would have a 4-dimensional world. But this is where our comfortable intuition starts to break down. What exactly is a 4th dimension? How can we even begin to understand something so alien to our experience? What would it mean for space to have 4 dimensions instead of 3? In order to understand this profound question, we need to first understand something fundamental about how dimensions are perceived. We need to examine the strange gap between the dimensions we live in and the dimensions we actually see. This gap will help us understand why the 4th dimension is so difficult to grasp. We live in a 3-dimensional world. That much is obvious. We move through 3 dimensions every day. We are 3-dimensional creatures in a 3-dimensional space. But here is the surprising truth. Despite living in 3 dimensions, we actually view things 2-dimensionally. Our perception of the world around us is fundamentally 2-dimensional, not 3-dimensional. Let me explain what this means. Take a perfect sphere as an example. Imagine a perfectly smooth sphere sitting in front of you. If you are looking at this sphere with your eyes, what do you actually see? You might think you see a 3-dimensional sphere, but that is not quite true. What you actually see looks just like a regular 2-dimensional circle. Your eye receives an image that is fundamentally flat. It is projected onto the back of your retina as a 2-dimensional image. The sphere appears as a circle on this flat surface. So how do you know it is actually a sphere and not just a flat circle? The only way that you can tell it is an actual sphere instead of a mere circle is because of the way light falls on it. The hues of light on the surface give you clues. The shading reveals the curvature. The way brightness changes across the surface tells your brain that this object has depth, that it curves away from you in 3-dimensional space. But the actual visual information entering your eye is still 2-dimensional. Your brain constructs the 3-dimensional interpretation from 2-dimensional visual data, plus additional clues like shading, shadows, and the way light behaves on the surface. And this is why the thought experiment about the sphere appearing as a circle is so important. When you look at a perfect sphere straight on, under uniform lighting, it truly does look circular. The 3-dimensional information is almost entirely contained in the shading pattern. If the lighting were somehow perfectly uniform from your point of view, if every point on the visible hemisphere of the sphere reflected exactly the same amount of light toward your eye, you genuinely could not distinguish it from a flat circle by vision alone. You would need additional information, perhaps from moving your viewpoint to see it from a different angle, or using binocular vision with both eyes, or reaching out and touching the object to feel its curvature. This same principle explains why photographs and paintings can be so convincing at depicting three-dimensional scenes. A photograph is literally two-dimensional. It is a flat piece of paper or a flat screen displaying an array of colored pixels. Yet it can show us a three-dimensional scene with remarkable fidelity because it recreates the two-dimensional patterns of light that our eyes would receive if we were looking at the real three-dimensional scene. A skilled photographer or artist can effectively fool our depth perception because they are reproducing the two-dimensional visual information that our brain relies on to construct three-dimensionality. Virtual reality technology takes this principle to its logical conclusion. VR headsets present slightly different two-dimensional images to each eye, mimicking binocular disparity. They track head movement and update the images accordingly, recreating motion parallax. They render proper perspective, shading, and occlusion. By carefully controlling all the two-dimensional depth cues, VR creates a convincing illusion of three-dimensional space, even though you are just looking at two flat screens inches from your eyes. This same principle applies in lower dimensions. Just like in a two-dimensional world, imagine that an organism in the two-dimensional world was looking upon a circle. This flat creature, living in a flat world, would perceive that circle in one dimension, but the light falling on that circle would give the creature information. The light would make the circle appear to be lighter at one end and darker in the middle, or darker at another end. These variations in brightness would tell the two-dimensional organism that the circle has curvature within its two-dimensional space, even though the organism is perceiving the scene in one dimension. And when this two-dimensional organism perceives its world in one dimension, think about what that means for understanding space. It must build up a mental model of its two-dimensional environment from a sequence of one-dimensional snapshots. As it moves through its world, it sees the scenery change. Things appear and disappear from its linear visual field. Objects become visible as lines and then vanish as it moves past them. The creature must remember these observations and stitch them together into a coherent map of its surroundings. Its brain must be doing something similar to what our brains do when we construct a three-dimensional model from two-dimensional visual input, but operating one dimension lower. There is another fascinating aspect to how we perceive our world. If an object is moving farther away from you or closer toward you, you do not actually perceive directly that it is getting closer or farther away. That is not what your eyes tell you immediately. Instead, what you see is that the object is getting smaller or larger in your field of vision. When something moves away, it appears to shrink. When something approaches, it appears to grow. And then your brain takes this information about changing size and makes an inference. Your brain interprets size changes and assumes that the object is getting either farther away or closer based on whether it appears smaller or larger. But this interpretation is not foolproof. Apparent size alone is ambiguous. An object could be small and close to you, or it could be large and distant, and in both cases, it might subtend the same visual angle, appearing the same size in your visual field. This is precisely why forced perspective tricks work so well in photography and filmmaking. You can make someone appear giant by positioning them close to the camera while placing other people far away. You can make someone look tiny by doing the reverse. The camera captures a two-dimensional image, and in that image, the relative sizes create an illusion about the three-dimensional arrangement. The famous photograph of a tourist appearing to hold up the Leaning Tower of Pisa uses this principle. The person is much closer to the camera than the tower, but by carefully positioning their hand, they create the illusion in the two-dimensional photograph that they are touching the distant tower. It is a perspective trick, playing with the fact that cameras capture two-dimensional projections of three-dimensional scenes. But here is a thought experiment that reveals how strange this really is. Let us say an object was able to grow in perfectly equilibrium with its motion. Imagine it was growing at exactly the same rate that it was shrinking in your vision as you move it farther away. Picture pushing something away from you, and as you push it away, it physically grows larger at exactly the rate needed to keep its apparent size constant in your vision. In this strange scenario, you would not be able to tell if there were no lights giving you depth information, or if there were no other details on the object that it was moving or growing at all. Without these additional clues, like perspective, shadows, or other depth cues, the object would appear completely stationary and unchanging. It would seem frozen in place, even though it was actually moving away and growing larger simultaneously. This reveals the fundamentally two-dimensional nature of our visual perception. If an object grows in size at precisely the rate that accounts for its increasing distance, the two effects cancel out. Its angular size in your vision remains constant. Without other depth cues, you might not notice it moving at all. This would be especially true if the object were viewed with one eye closed, eliminating binocular vision in uniform lighting that provides no shading information against a blank background that provides no reference points. The growth and the motion in depth become invisible because they exactly compensate each other in the two-dimensional projection your eye receives. This thought experiment could actually be demonstrated with modern technology. Imagine a screen that displays a circle. As you move away from the screen, the system tracks your distance using sensors and proportionally increases the size of the circle displayed. If calibrated perfectly, the circle would maintain constant angular size in your visual field despite your movement. Without other cues, you might not realize you were moving at all. The circle would appear stationary and unchanging. Now, you may have assumed, following this logic, that since we perceive things in 2 dimensions, despite living in 3 dimensions, a 2-dimensional organism would see in 1 dimension, and you would be correct in that assumption. This pattern continues down the dimensional ladder. Just as we 3-dimensional beings perceive a 2-dimensional projection of our 3-dimensional world, a 2-dimensional being would perceive a 1-dimensional projection of its 2-dimensional world. Let me illustrate this with another example. Imagine we are watching a rubber band expand. This rubber band is sitting on a flat surface in a 2-dimensional world. As it moves farther away from a little organism in the 2-dimensional world, something interesting happens. The rubber band is growing at exactly the same rate that it is moving farther away. It expands outward as it moves backward. This 2-dimensional organism does not actually perceive that anything is happening to the rubber band at all. From its perspective, constrained to 1-dimensional vision, the rubber band appears unchanged. It seems stationary. The growth and the motion perfectly cancel each other out in the creature's 1-dimensional perception. But we can see what is really happening. Since we can actually observe this scene from our 3-dimensional world, and we perceive things in 2 dimensions, we can see the situation for how it actually is. We can watch the rubber band expanding. We can watch it moving away. We can see both changes happening simultaneously because we have that extra dimension of perception that the 2-dimensional organism lacks. This thought experiment transfers perfectly down to 2 dimensions. A 2-dimensional organism watching a circle grow while moving away would face the exact same perceptual challenge. The circle occupies some extent in the 1-dimensional visual field of the creature. As the circle moves away in the 2-dimensional world, it should subtend a smaller angle, appearing smaller in the creature's 1-dimensional view. But if the circle physically grows to compensate for its increasing distance, the creature perceives no change. The circle seems static, unchanging, even though 2 separate things are happening to it. Meanwhile, we, observing from our three-dimensional perspective, can see the full two-dimensional plane where this is happening. We can see the circle growing. We can see it moving away. We have that extra dimension of perception that makes everything clear. We are not limited to the one-dimensional view that the two-dimensional creature has. We can see the complete picture because we are observing from a higher dimension. The reason that the two-dimensional organism does not see things the way they really are comes down to this fundamental principle. The two-dimensional organism sees things in one dimension, just as we three-dimensional creatures see things in two dimensions. Each type of creature perceives reality in one fewer dimension than the space it actually inhabits. So in a very real way, we do not actually see our world the way it truly is. We see a flattened, two-dimensional projection of a three-dimensional reality. Our brains do an excellent job of reconstructing the three-dimensional world from this two-dimensional information, using clues like perspective, lighting, shadow, binocular vision, motion parallax, and our accumulated knowledge of how objects behave. But the raw visual data coming into our eyes is fundamentally two-dimensional. We are interpreting a projection, not seeing reality directly. This has profound philosophical implications. It means that our experience of the world is filtered through our perceptual apparatus. We do not have direct access to objective reality as it truly is. We have access to a processed, interpreted version of reality that our brains construct from limited sensory data. We see two-dimensional projections of a three-dimensional world, and our brains infer the third dimension. This insight troubled philosophers for centuries. How can we know anything about reality if all we have access to is our subjective perception? Immanuel Kant distinguished between the thing in itself, noumenon, and the thing as we perceive it, phenomenon. We can never know the thing in itself directly, only the phenomenon, the appearance, filtered through our senses and processed by our minds. But science has given us tools to go beyond our direct perception. We can measure things we cannot see. We can infer structures we cannot visualize. We can understand dimensions we cannot perceive. This is the great power of mathematical reasoning. It extends our knowledge beyond the limits of our senses. Now, here is where things become truly mind-bending. A four-dimensional creature, however, seeing our three-dimensional world in three dimensions, would be able to see through things. Let that sink in for a moment. A being from the fourth dimension, looking at our three-dimensional space, would perceive it the same way we perceive a two-dimensional plane. Just as we can see everything on a flat surface all at once, a four-dimensional being would be able to see absolutely everything in our three-dimensional space all at once. Think about how we can observe a two-dimensional environment. Imagine several organisms spread along a two-dimensional environment on your floor. Perhaps you have drawn a little two-dimensional world on a piece of paper with houses and creatures and walls separating different areas. From your three-dimensional perspective, looking down at this paper, you can see everything simultaneously. You can see inside all the houses at once. You can see every organism, no matter where it tries to hide. No wall can block your view because you are observing from a higher dimension. The walls exist in the two-dimensional plane, but you are looking from above, from the third dimension, and you simply see over and around those walls. A four-dimensional creature would have this exact same advantage when looking at our three-dimensional world. It would be able to see inside houses, seeing through all the walls as if they were not there. It would be able to see inside of people, viewing your internal organs, your bones, your brain, everything simultaneously. No barrier in our three-dimensional space could hide anything from a four-dimensional observer. Privacy, as we understand it, would be meaningless to such a being. Every secret would be visible. Every hidden thing would be exposed. Consider what this means more carefully. When you look at a map, a floor plan of a building, you can see every room simultaneously. Walls do not block your view because you are looking from above, from the third dimension, perpendicular to the two-dimensional floor plan. You see the entire layout at once. Interior rooms are just as visible as exterior rooms. Secret passages are immediately obvious. Hidden rooms cannot hide from you. You have a God's eye view of the two-dimensional structure. Imagine being a two-dimensional creature trying to create privacy in such a world, knowing that three-dimensional beings could be watching. You could build walls in your two-dimensional plane, creating rooms and enclosures. From the perspective of other two-dimensional beings, these walls work perfectly. They create hidden spaces, private areas where you cannot be seen. But to any three-dimensional observer looking down at your world, all your walls are meaningless. Your private spaces are completely open to observation. You might as well be living in a glass house, except even glass would not help, because the three-dimensional being is not looking through your walls. They are looking at your plane from a direction that does not pass through the walls at all. A four-dimensional being looking at our three-dimensional world would have the same advantage. Your house would be completely transparent to them, not transparent in the sense that your walls are made of glass, but transparent in the sense that they can see from a direction you cannot point to, a direction that bypasses your walls entirely. The inside and outside of your house are equally visible to them because they can observe from a four-dimensional vantage point. Your body would be equally transparent. Your skin does not hide your insides from a four-dimensional being. They can see your skeleton, your organs, your circulatory system, your nervous system, all simultaneously, all at once. Not through X-ray vision in the science fiction sense, where electromagnetic radiation penetrates through your body, but simply through ordinary four-dimensional vision, observing a three-dimensional object from a four-dimensional vantage point. Imagine the implications if four-dimensional beings actually existed and could observe our world. No vault would be secure. No safe could protect its contents. No military could hide its secrets. No person could have privacy. Everything in our three-dimensional space would be completely open to inspection from the fourth dimension. This seems like a profound violation of privacy, but from the four-dimensional perspective, it would be no more strange than us looking down at a map and seeing all the rooms at once. This seems bizarre and violating to us because we treasure privacy and we rely on three-dimensional barriers like walls and clothing and closed doors to provide that privacy. But these barriers only work against other three-dimensional beings. They are completely ineffective against a higher dimensional observer. It is as if you try to hide something by drawing a circle around it on a piece of paper. You have successfully enclosed the object in two dimensions. You have created a two-dimensional barrier, but anyone in three dimensions can simply look down and see inside the circle. The circular boundary provides no concealment from a higher dimensional perspective. There is something philosophically profound here about the nature of privacy and enclosure. These concepts are dimension dependent. What is enclosed in n dimensions might be completely open when viewed from n+1 dimensions. A lock and key work in three dimensions because the internal mechanism of the lock is hidden inside the three-dimensional structure of the lock body, accessible only through the specific pathway that the correct key can navigate, but they would be trivial to bypass from four dimensions. A four-dimensional being could reach into a locked safe without opening it, without breaking it, by reaching in from the fourth dimension, from a direction that goes around the three-dimensional walls of the safe without ever passing through them. The locks and walls exist only in three dimensions. They provide no barrier in four dimensions. Of course, We have no evidence that four-dimensional beings exist. This is all hypothetical, a thought experiment to help us understand what the fourth dimension would mean if it did exist. But it helps us understand the relationship between dimensions. It helps us see how a higher dimension provides a vantage point from which lower dimensional structures become transparent and accessible in ways that seem impossible from within those lower dimensions. Now let us think about the structure of dimensions themselves more systematically. Let us think about how they are built up from each other. If a two-dimensional world, which is essentially a flat surface, is made up of an infinite amount of lines stacked together, then following this pattern, the three-dimensional world is made up of an infinite amount of two-dimensional planes stacked together. We have already discussed this principle. It is mathematically rigorous and is used in calculus all the time. So continuing this logical progression, the four-dimensional world would logically be made up of an infinite amount of three-dimensional objects stacked together. But here is something crucial to understand. They are not just put together like building blocks that you would stack next to each other in ordinary three-dimensional space. That would not create a four-dimensional world. That would just be three-dimensional space again, just filled with many objects arranged in three-dimensional space. The four-dimensional world is something fundamentally different. The stacking happens in a direction we cannot point to. It happens in a direction that does not exist in our three-dimensional space. Just as the two-dimensional plane cannot point in the direction of height, we cannot point in the direction of the fourth dimension. It is perpendicular to all three of our dimensions simultaneously, which is something we cannot visualize or even properly imagine. This is where language starts to fail us completely. How do we arrange three-dimensional volumes adjacent to each other in a new direction? In our three-dimensional experience, adjacent means next to each other in one of our three dimensions, either to the left or right, or forward or backward, or up or down. But the fourth dimension is perpendicular to all three of our dimensions at once. It is a direction that does not exist in our space, so we cannot point to it. We cannot demonstrate it physically. We cannot show you where it is. We can only reason about it mathematically and logically. It is like trying to explain the concept of up to a being that lives in a truly two-dimensional universe, a creature that has never experienced the third dimension. Up is perpendicular to their entire plane. They can point forward and backward within their plane. They can point left and right. But they cannot point up because up does not exist in their space, not in any direction they can access or gesture toward. The best we could do is tell them that up is a third direction, different from their two directions, perpendicular to both of them simultaneously, and that it allows three-dimensional beings to move in ways that two-dimensional beings cannot. If we tried to describe up to this two-dimensional being, they might ask, "Which way is up? Show me." And we would have to say, "I cannot show you within your plane." Up is not a direction in your plane. It is a new direction, outside your plane, perpendicular to every direction you can point to. This would be deeply frustrating for the two-dimensional being. They might conclude that up is meaningless nonsense, that we are talking about something that does not exist. But we know up exists. We experience it. We move through it. It is simply beyond their ability to perceive or conceive. The fourth dimension is the same for us. It is perpendicular to forward, backward, left, right, and up, down, all at once. It is a direction we cannot point to and cannot move in, at least not in ways we currently understand or can access. In order to understand this better, we need to understand the logical progression of mathematics in our world. We need to see how basic shapes evolve as we add dimensions. Let me show you this progression step by step, because it will illuminate how dimensions build upon each other in a very structured, predictable way. Imagine that a simple straight piece represents the first dimension. It is simply a straight line segment, which is basically what the first dimension looks like. This line has length, but no width and no height. It is one-dimensional. This is the fundamental building block, the simplest geometric object that has extension in space. It stretches from one point to another, defining a direction and a distance, but nothing more. Now, if you take this line segment and you add 3 more of these straight lines and connect them together so that adjacent sides are perpendicular to each other and opposite sides are parallel to each other, what do you get? You end up with the basic shape of the second dimension. You have created a square, 4 lines of equal length connected at right angles, forming a closed 2-dimensional shape. This square lives fully in 2 dimensions. It has length and width, but no height. It is flat. It is the natural extension of the line segment into 2-dimensional space. The square has certain properties we should note. It has 4 sides, edges, all of equal length. It has 4 vertices, corners, where pairs of edges meet. At each vertex, exactly 2 edges meet, and they meet at right angles. The square has symmetry. It looks the same if you rotate it 90 degrees. It has area, which the line segment does not. The square is qualitatively different from the line segment because it encloses a 2-dimensional region of space. Now, if you keep going from here, if you continue this pattern into the 3rd dimension, you add more squares to your existing square. You extend it into the 3rd dimension so that there are a total of 6 squares, all connected together. All adjacent sides, the sides that meet at edges, are perpendicular to each other. And all opposite sides, the sides that face each other across the shape, are parallel to each other. What do you end up with? Obviously, you end up with a cube. A perfect 3-dimensional cube has 6 square faces, 12 edges where pairs of faces meet, and 8 vertices where 3 edges come together. It is the natural extension of the square into 3-dimensional space. Let us pause here and appreciate the structure of the cube more carefully. Each vertex has exactly 3 edges meeting at it, corresponding to the 3 dimensions of space. Each edge is shared by exactly 2 faces. Each face is a square. The cube has volume, which neither the line segment nor the square possesses. The cube has multiple types of symmetry. You can rotate it in various ways and it looks the same. The cube is a beautiful object, both mathematically and aesthetically. It has appeared in art and architecture throughout human history. The Kaaba in Mecca, one of the most sacred sites in Islam, is approximately cubic. Dice are cubes. The mathematical perfection of the cube, with all its edges equal and all its angles right angles, has made it a symbol of solidity, stability, and order. So if you tried to keep going from here, if you wanted to extend this pattern one more step, you would create a 4-dimensional basic shape. You would have what is called a tesseract, also sometimes known as a hypercube. This is the 4-dimensional analogue of the cube, just as the cube is the 3-dimensional analogue of the square, and the square is the 2-dimensional analogue of the line segment. Now, I cannot show you what a real tesseract looks like. This is fundamentally impossible for reasons we will discuss, but you need to understand the basic principle of how it is constructed. A tesseract is essentially composed of 8 cubes that are connected together in 4-dimensional space. Just as a cube has 6 square faces, a tesseract has 8 cubic faces, or, more properly, cells. Every adjacent cell, every pair of cubes that meet at a square face, are perpendicular to each other in 4-dimensional space. And all opposite cells, cubes that face each other across the tesseract, are parallel to each other. The structure becomes more complex. A A tesseract has 16 vertices. At each vertex, 4 edges meet instead of 3. It has 32 edges in total. It has 24 square faces, and it has 8 cubic cells. These numbers follow patterns that extend from lower dimensions. The number of vertices doubles when you add a dimension. A line segment has 2 endpoints. A square has 4 corners. A cube has 8 vertices, and a tesseract has 16 vertices. Yet here is something strange about a tesseract. There are 4 lines connecting to each vertex, each corner point of the tesseract, rather than the 3 lines that meet at each corner of a regular cube. This is because the tesseract exists in 4 dimensions. At each vertex, you can move in 4 mutually perpendicular directions, not just 3. These 4 directions are the 4 dimensions of space the tesseract inhabits. If we try to project a tesseract into our 3-dimensional space, and then represent that 3-dimensional projection on a 2-dimensional screen or paper, a tesseract would look somewhat like a certain picture you might have seen. You might have seen images of a small cube sitting inside a larger cube, with their corners connected by diagonal lines. That is one common way to depict a tesseract in a projection that we can see. But understand this clearly and emphatically. That picture is not exactly what a tesseract looks like. That cannot be what it actually looks like, because what you are seeing is a 2-dimensional depiction of a 3-dimensional projection of a 4-dimensional object. We have lost information twice in this process of projection. The tesseract has been projected from 4 dimensions down to 3 dimensions, losing information in that step, and then projected again from 3 dimensions down to 2 dimensions so we can see it on a screen or paper, losing more information in that second step. Obviously, not all the lines in that picture are straight in 4-dimensional space, even though some appear bent or angled in our projection. The angles are not what they seem. The proportions are distorted. Edges that are actually the same length in 4 dimensions appear as different lengths in the projection. Cells that are actually the same size appear as a small cube nested inside a larger cube. But this size difference is purely an artifact of the projection, like how a cube drawn in perspective on paper shows a small square inside a larger square, even though all the faces of the real cube are the same size. I cannot show you what a tesseract actually looks like in its true 4-dimensional form, because we cannot perceive things truly in 3 dimensions. Remember, we perceive in 2 dimensions, and we certainly cannot perceive the 4th dimension at all. More than that, you cannot even imagine what a tesseract looks like in its true form. You cannot physically picture it in your mind. You cannot visualize the 4th dimension or any 4-dimensional shape in its true form. Your brain is not equipped for this. Your mind evolved to navigate 3-dimensional space and perceive 2-dimensional projections of that space. The 4th dimension is beyond the reach of your imagination, beyond the reach of your visual intuition. You can think about it mathematically. You can understand it through equations and logical reasoning, but you cannot picture it. You cannot hold an image of a true tesseract in your mind's eye. And this is not a failing on your part. This is not because you are not smart enough or have not thought about it hard enough. It is because human brains are not built for 4-dimensional visualization. Our visual cortex, the part of our brain that processes visual information and creates our mental imagery, evolved to handle 3-dimensional space as experienced through 2-dimensional vision. It is not designed to directly visualize objects in higher dimensions. When you imagine a cube in your mind, you are not really seeing a full 3-dimensional cube in some higher dimensional mental space. You are imagining different 2-dimensional views of a cube, perhaps mentally rotating it to see different faces, simulating how it would look from different angles. But your mental image is still composed of two-dimensional projections. You simulate 3 dimensions by imagining multiple views and how they relate to each other, but you do not hold a true 3-dimensional image in a higher dimensional visual space. Your imagination, like your vision, operates on 2-dimensional representations. We simply do not have the neural architecture for true 3-dimensional visual imagination, let alone 4-dimensional visualization. Our entire visual system, from the retina through the optic nerve to the visual cortex and beyond, is built around processing 2-dimensional images. Evolution shaped our brains to be very good at this specific task because it is what we need to navigate our world. But it did not equip us with the ability to visualize higher dimensional spaces because there was no evolutionary advantage to that capability. We do not move through 4-dimensional space, so we have no neural machinery for visualizing it. So when I say you cannot imagine a tesseract, I mean this quite literally and precisely. You can think about its properties. You can list its characteristics: 16 vertices, 32 edges, 24 faces, 8 cells. You can manipulate equations describing it. You can reason about it logically, following the patterns from lower dimensions, but you cannot hold a true visual image of it in your mind's eye. Your brain is simply not capable of that kind of visualization. And this is not unique to you. No human being can truly visualize a tesseract or any 4-dimensional object. We are all limited by the same fundamental constraints of our neurobiology. And the progression does not stop there. You can keep going beyond the 4th dimension even further. You can extend these concepts to the 5th dimension. You can go to the 6th dimension. You can go to the 71st dimension if you want. You can go as high as you can imagine counting. It does not matter how high you go. Theoretically, there are an infinite amount of spatial dimensions possible. Each one is perpendicular to all the ones before it in ways we cannot visualize or point to. Each one extends space in a new direction that does not exist in the lower dimensions. And this continues to higher dimensions as well. A 5-dimensional hypercube would have 32 vertices, 80 edges, 80 square faces, 40 cubic cells, and 10 tesseractic facets. That is right, a 5-dimensional hypercube has tesseracts as its 4-dimensional faces. Each vertex would have 5 edges meeting at it. The structure becomes increasingly complex, increasingly impossible to visualize in any intuitive sense, but it follows logical, mathematical patterns that we can describe precisely and work with rigorously. Mathematicians work with high-dimensional spaces all the time in their research. They do not try to visualize them in any ordinary visual sense. Instead, they manipulate equations and follow logical rules. They think about properties and relationships. They prove theorems about objects they cannot picture. They navigate these abstract spaces using algebraic tools and geometric intuition that does not depend on literal visualization. This is the power of mathematical abstraction. We can understand things rigorously, can work with them precisely, can discover truths about them, even when we cannot visualize them in our mind's eye. A space can have any number of dimensions mathematically. 7-dimensional space is perfectly well defined. 71-dimensional space, as mentioned earlier, is equally valid. A million-dimensional space is mathematically coherent. There is nothing special about 3 dimensions from a pure mathematics standpoint, even though 3 dimensions is profoundly special to us because we live in it and our entire intuition is built around it. In many areas of physics and mathematics, high-dimensional spaces are routine, even mundane. In quantum mechanics, the state of a system with many particles is described by a vector in a space called Hilbert space, which can have a huge number of dimensions, possibly thousands or millions of dimensions, depending on the system. A system with n particles, where each particle can be in one of m states, requires a space with n dimensions to fully describe. This grows exponentially. For just 10 particles with 10 possible states each, you need 10. 10 equals 10 billion dimensions. In data science and machine learning, datasets are often treated as points in high-dimensional spaces where each dimension corresponds to a different measured variable or feature. A dataset with 100 different measurements per data point lives in a 100-dimensional space. When you analyze this data, looking for patterns or clusters, you are working in a 100-dimensional space. These spaces are impossible to visualize in any traditional sense, but they are very useful for calculations and for understanding patterns in data. Machine learning algorithms routinely work in spaces with thousands or even millions of dimensions. An image with 1000 times 1000 pixels has 1,000,000 pixels and can be thought of as a point in a 1,000,000-dimensional space where each dimension corresponds to the brightness or color of one pixel. Machine learning algorithms can find patterns in this 1,000,000-dimensional space that would be completely invisible to human analysis. So theoretically, there is no upper limit to the number of dimensions space could have. Space could be 10-dimensional, or 20-dimensional, or 1,000-dimensional. From a pure mathematics perspective, there are infinitely many possible numbers of dimensions, and mathematicians study spaces of all these different dimensionalities. But in our physical universe, it appears that we have 3 spatial dimensions plus time. Why 3? Why not more? Why not fewer? This is actually a deep question in physics, one that does not have a completely satisfactory answer yet. Some theories, like string theory, propose that there might be additional spatial dimensions beyond the 3 we experience, but these extra dimensions would be curled up incredibly small, compactified at tiny scales, too minuscule for us to notice in everyday life. They would be rolled up at scales far smaller than an atom, possibly at the Planck length, which is about 10⁻⁵ meters, incomprehensibly tiny, far smaller than anything we can measure directly. The Planck length is derived from fundamental constants of nature, the speed of light, the gravitational constant, and Planck's constant. It represents a scale at which quantum effects of gravity become important, where the smooth fabric of space-time breaks down into quantum foam. At this scale, our current theories of physics become inadequate. We do not have a complete theory of quantum gravity that can describe what happens at the Planck scale. If these extra dimensions exist, particles and forces would have limited freedom to move through them because of how tightly they are curled up. It would be like living on the surface of an extremely thin wire. You have a lot of freedom to move along the length of the wire, but very little freedom to move around its circumference. Meanwhile, the 3 dimensions we know are extended, allowing movement over vast distances, from microscopic scales to cosmic scales. So we perceive 3 spatial dimensions not because there are only 3 in total, but because 3 are large and accessible while any others are minuscule and hidden, curled up so small that we cannot detect them even with our most sensitive instruments. This is speculative, of course. We do not have direct experimental evidence for these extra dimensions. Physicists have looked for signs of them in particle accelerator experiments, looking for particles disappearing into extra dimensions or for the influence of extra-dimensional gravity, and have not found them yet. But absence of evidence is not evidence of absence, especially when we are looking at such tiny scales. It is an example of how physicists think seriously about the possibility of higher dimensions existing in our actual universe, not just as mathematical abstractions. Now, there is a common misconception about the 4th dimension that we need to address thoroughly and carefully. Many people believe that the 4th dimension is time. You have probably heard this idea before, perhaps many times. It is repeated often in popular science discussions, in science fiction stories, in casual conversations about physics. Some people confidently assert that time is the fourth dimension, and that when we talk about four-dimensional space, we are talking about three spatial dimensions plus time, which together form space-time. The reasoning goes something like this. By going forward and backwards in time, if you move forward the same distance and then backwards the same distance, you end up in the same place you started, just like moving along a spatial dimension. And while that may seem logical at first glance, if you think about it carefully and critically, it really does not make sense. There are several serious problems with identifying the fourth dimension with time. If you imply that the fourth dimension is actually time, well, first of all, time is not spatial. This is a fundamental distinction. There is a profound difference between space and time, quite obviously. Space is a thing we move through. We can go forward in space and then go backward in space. We can stand still in space. We can choose our direction of movement through space. Time is something that flows, something we move through involuntarily, or perhaps something that moves through us. The metaphors become unclear and imprecise. The key point is that we cannot stop moving through time. We cannot reverse our direction in time. We cannot stand still in time. We are always moving forward through time at a rate of 1 second per second. Time has properties that are fundamentally different from spatial dimensions. And if we assume that all dimensions follow according to a pattern, which is what we have been discussing throughout this entire exploration, then calling the fourth dimension time does not really make sense. Think about it this way, carefully and systematically. Every dimension has time in it. One-dimensional space exists in time. That one-dimensional creature we imagined, sliding back and forth on its line, experiences time passing. Events happen one after another for it. Two-dimensional space exists in time. Those flat creatures can move around their plane, and they experience time flowing, events unfolding sequentially. Three-dimensional space exists in time. We experience time constantly. Time is present in all dimensions, in all spatial configurations, regardless of how many spatial dimensions there are. So saying that the fourth dimension is time would mean that the fourth dimension is special in some unique way. It would break the pattern we have been following. It would be different in kind from all the other spatial dimensions. And that does not make sense if we are following the logical progression we have been discussing. Each spatial dimension should be similar to the others, just adding a new perpendicular direction of movement through space. Time does not fit this pattern. Time is not just another direction we can move in space. It is something else entirely. Moreover, the whole pattern we have been discussing about dimensions, about stacking lower dimensional spaces to create higher dimensional spaces, about objects in dimension n, perceiving in dimension n-1. This pattern applies to spatial dimensions. It does not apply to time in the same way. A four-dimensional spatial being would perceive three-dimensional space, seeing everything in our three-dimensional world the way we see everything on a two-dimensional surface. But a being that experiences time does not thereby perceive three-dimensional space. Time is not about perception in the same way that spatial dimensions are. Time is about change, about causality, about before and after, about the sequencing of events. It is a fundamentally different aspect of reality than spatial extension. Another reason this identification does not make sense is related to the way time interacts with space and motion in our universe, according to Einstein's theories. We actually travel through time at different rates depending on how we move through space. This is one of the strange predictions of Einstein's theory of relativity, and it has been confirmed by many precise experiments over the past century. We very, very, very slightly travel through time at different rates whenever we move, due to relativistic effects that become significant at high velocities. Let me give you a more dramatic example to illustrate this clearly. If a group of astronauts were to get into a spaceship and they were able to accelerate this spaceship very, very close to the speed of light, say 99.9% of light speed, something remarkable would happen. Time would slow down for them relative to people on Earth. This is called time dilation, and it is a real, measurable effect. If they went around in this nearly impossible spacecraft that could somehow travel very close to the speed of light, and they journeyed through space at this incredible velocity for a few months by their own clocks, experiencing 6 months passing inside the ship, and then afterwards they returned to Earth, they would find something shocking. Earth would have actually progressed forward through several years, perhaps many years, perhaps decades, depending on exactly how fast they were traveling. They would have moved forward in time relative to Earth by moving that quickly through space. They might have experienced only 6 months passing inside their ship, aging only 6 months, but their friends and family on Earth would have aged by several years or more. This is a real effect that has been measured with atomic clocks on aeroplanes and satellites. Clocks on GPS satellites, orbiting Earth at high speeds, tick at a slightly different rate than clocks on Earth's surface. The GPS system must correct for this relativistic time dilation, or the positioning would drift out of accuracy within hours. Time is not absolute. It is flexible. It is relative. It depends on your reference frame. It is connected to motion and space in ways that a simple spatial dimension is not. This reveals that time is something fundamentally different from a spatial dimension. You can move forward and backward freely in a spatial dimension. You can choose your direction. You can choose your speed. You can stop, but in time, you always move forward, inexorably. And your rate of movement through time depends on how you move through space and on the gravitational field you are in. This is not how spatial dimensions behave relative to each other. Moving along one spatial dimension does not change your rate of movement along another spatial dimension. Moving north does not make you move faster or slower east. But moving through space does change your rate of movement through time. When astronauts travel very fast, close to the speed of light, they age more slowly relative to people who remain stationary on Earth. If they travel for 6 months by their own clocks and then return, they might find that years have passed on Earth. They have jumped forward into Earth's future, in a sense. They aged only 6 months, while everyone on Earth aged several years. This is not the same as moving through a spatial dimension. They cannot go back. They cannot undo this effect easily by simply traveling in the opposite direction. They have taken a one-way trip into the future. And this happened not because they moved through a fourth spatial dimension, but because time itself is relative, because different observers can disagree about how much time has passed, depending on their relative motion and the gravitational fields they experience. Now, in relativity theory, space-time is indeed treated as a four-dimensional construct. Events happen at particular locations in space and particular moments in time. An event can be labelled with 4 coordinates: 3 for its position in space, perhaps x, y and z coordinates, and 1 for when it happens, a time coordinate t. In this sense, space-time is four-dimensional, and this is a useful and physically accurate way to think about the structure of our universe according to modern physics. But space-time's time dimension is fundamentally different from the spatial dimensions. The mathematics treats it differently, in a very specific way. In the equations of special relativity, the time coordinate appears with an opposite sign compared to the spatial coordinates in the space-time interval formula. The space-time interval between two events is given by a formula like delta squared equals c delta squared minus delta squared minus delta squared minus delta squared, where the time term is positive and the spatial terms are negative, or vice versa depending on the sign convention used. This opposite sign is crucial. It reflects the fundamental difference between time and space. Time is not just another spatial dimension with a different label. It has different mathematical properties built into the structure of space-time. It has a different signature in the metric that describes the geometry of space-time. This mathematical difference has real physical consequences for how particles move, how light propagates, how causality works. You can move forward or backward freely in space. You can stand still in space relative to some reference frame. But you cannot stop moving through time. You always move forward through time at some rate, and that rate depends on your motion through space and the gravitational field you are in, according to general relativity. This is profoundly different from how spatial dimensions work. Furthermore, the geometry of space-time has a different character than the geometry of purely spatial dimensions. Space-time has what is called a Lorentzian signature, or pseudo-Riemannian metric, with one negative term corresponding to time and three positive terms corresponding to the three spatial dimensions in its metric, or vice versa, depending on sign convention. A purely four-dimensional spatial geometry would have all positive terms, giving it a Euclidean or Riemannian metric. This mathematical difference reflects physical reality. Space-time has a light cone structure with time-like, space-like, and light-like intervals, determining what events can influence each other. Purely spatial dimensions do not have this structure, so while it is technically correct to say that space-time is four-dimensional, combining three dimensions of space with one dimension of time, it is misleading and confusing to say that time is simply the fourth dimension in the same sense as a fourth spatial dimension. They are different kinds of dimensions, with different properties and different roles in physics. When physicists talk about the fourth dimension in the context of spatial geometry, they usually mean a fourth spatial dimension, not time. Time is something else, something orthogonal to the discussion of how many spatial dimensions exist. So when discussing the fourth dimension in the context of geometry and spatial reasoning, as we have been doing throughout this exploration, we should think of it as a fourth spatial dimension, not as time. Time can coexist with any number of spatial dimensions. A one-dimensional space exists in time. A two-dimensional space exists in time. A three-dimensional space exists in time. A four-dimensional space would also exist in time, just as it would exist in a four-dimensional spatial configuration. Time is orthogonal to the whole discussion of spatial dimensions, in a sense perpendicular to the entire question we are exploring. The time dilation example with astronauts traveling near the speed of light illustrates that time is strange and flexible and deeply connected to space through Einstein's relativity. But this strangeness is not the same as being a spatial dimension. Time dilation occurs because of motion through space and because of gravitational fields. It is a relationship between space, time, matter, and energy, as described by Einstein's theories of special and general relativity. It does not make time equivalent to or interchangeable with a spatial dimension. Now, there is another interesting and speculative concept involving the fourth dimension that many physicists, cosmologists, and mathematicians have discussed over the years. Some suggest that dimensions might be very, very slightly curved. This is a profound idea that changes how we think about the nature of space itself, and it has implications for whether dimensions extend infinitely or wrap back on themselves, for whether the universe is finite or infinite in extent. If you really think about it carefully, perhaps nothing can be truly absolutely infinite. Infinity is a useful mathematical concept, a tool that helps us reason about limits and extreme cases, about what happens as quantities grow without bound. But in physical reality, actual infinity might not exist. It is possible that everything that physically exists is finite, finite in extent, finite in duration, finite in every measurable quantity. So imagine that the first dimension, that simple line we started with, is not actually infinitely straight and infinitely long, extending forever in both directions. Imagine instead that it is just very, very slightly curved. The curvature is so subtle, so gentle, so gradual that you would never notice it in any ordinary circumstance. The line appears perfectly straight over any distance you could measure with any instrument we possess. But it is there, this tiny curvature, imperceptible yet real. If this line is curved, then after a very, very long distance, after travelling immensely far along this line, perhaps farther than we could ever practically travel, farther than the observable universe, it would eventually curve back on itself. It would end up creating a circle, or more precisely, a one-dimensional closed loop. A one-dimensional space that curves around in the second dimension forms a circle. The line never ends in this scenario. It just wraps around to meet itself. If you travel in one direction long enough, consistently in what seems like a straight line, you come back to where you started, approaching from what you perceive as the opposite direction. As suggested by many physicists and cosmologists who study the large-scale structure of the universe, if you keep traveling in the same direction in our universe, maintaining a straight line, never deviating, you might eventually end up where you started after a very, very long amount of time and distance. Obviously, the distances involved would be staggeringly huge, perhaps larger than the observable universe, perhaps vastly larger. We cannot see far enough to know for sure. But in principle, if space is curved in this way, if the universe has a closed topology, you could travel in a straight line forever and eventually return to your starting point, like an ant walking around the surface of a sphere, going in what seems like a straight line on the surface, but eventually completing a circuit. The same thing would happen to the second dimension if it follows this pattern. If you take a flat two-dimensional plane and then you extend it outward and allow it to curve very, very slightly in the third dimension, it will eventually make a sphere. A two-dimensional surface that curves in three-dimensional space forms a sphere. This is actually how we think about the surface of Earth. Earth's surface is approximately two-dimensional. We ignore small variations in height, like mountains and valleys, treating it as a smooth surface, and it curves through three-dimensional space to form a sphere. If you travel in one direction on Earth's surface long enough, maintaining your heading, you come back to where you started. You circumnavigate the globe, proving that the surface wraps around on itself. The simplest two-dimensional closed curved space is the surface of a sphere. If you are a two-dimensional being living on the surface of a sphere, you can move in any direction on this surface. You can head in any direction you choose. You never reach an edge. You never fall off. There is no boundary, no border where the surface ends, no place where you could step off into some void. But if you travel far enough in a straight line along the surface, following a geodesic, the curved space equivalent of a straight line, you will eventually return to your starting point. The surface has a finite area. You could measure it, calculate the total surface area of the sphere, but no boundary, no edge. It is curved in 3 dimensions, but the being living on it does not experience that 3rd dimension directly. It just experiences the 2-dimensional surface wrapping around on itself. This is actually how we think about the surface of Earth from a geometric perspective. We are not truly 2-dimensional. Of course, we have height. We stand up from the surface. We build tall structures. But ignoring the radial dimension, Earth's surface is approximately 2-dimensional. It curves through 3-dimensional space, forming a sphere. We can travel in any direction on the surface, and if we go far enough, we come back to where we started. Ancient explorers proved this empirically by circumnavigating the globe, sailing west from Europe and eventually arriving back from the east. They sailed continuously in one direction and looped back to their starting point, demonstrating conclusively that Earth's surface is closed and finite. And the same principle applies to our 3-dimensional space, if it follows this cosmic pattern. Our 3-dimensional space might curve very, very slightly in the 4th dimension. It would form what we might call a 3-sphere or a hypersphere, sometimes written as S cubed in mathematical notation. It is a 3-dimensional surface that curves through 4-dimensional space. If this is true, then our 3-dimensional universe, if you travelled far enough in a straight line in any direction through space, never turning, never deviating, you would eventually curve around in 4-dimensional space and return to your starting point. The universe would be finite in extent but boundless, without boundary. You could never reach an edge, could never find a boundary or a wall where space ends, but you could not travel infinitely far without retracing your path, without coming back to where you started. For 3 dimensions, the analog is called a 3-sphere or hypersphere. This is harder to visualize because it would be a 3-dimensional surface curving through 4-dimensional space, and we cannot visualize 4-dimensional space at all. But mathematically, it is perfectly well defined, completely coherent. It would be a 3-dimensional space with finite volume, but no boundary, no edge, no where that space stops. If you travelled in a straight line in any direction long enough, never turning, maintaining your heading forever, you would eventually return to your starting point, having completed a circuit through the universe. Our actual universe might have this geometry, or something like it. The universe might be finite in extent, but unbounded, wrapped up on itself in 4-dimensional space. If you pointed your spaceship in any direction and travelled forever in a straight line, never turning, accelerating indefinitely at relativistic speeds, you might eventually return to where you started, having circled the entire universe like circumnavigating Earth, but in 3 dimensions through 4-dimensional space instead of 2 dimensions on a 2-dimensional surface. Alternatively, the universe might be flat, extending infinitely in all directions in a Euclidean geometry, with parallel lines remaining parallel forever, never converging or diverging. Or it might be open, with a hyperbolic geometry and negative curvature, also extending infinitely, but with space expanding faster than flat Euclidean space, with parallel lines diverging as they extend. We do not know for certain which geometry describes our universe at the largest scales. Current astronomical observations, including measurements of the cosmic microwave background radiation from the early universe, are consistent with a flat or nearly flat universe, but some curvature is possible within observational uncertainty. The universe appears to be very close to flat on large scales, but whether it is exactly flat or slightly curved remains an open question in cosmology. The data from the Planck satellite and other cosmic microwave background experiments suggest that if the universe is curved, the radius of curvature must be enormous, much larger than the observable universe. Within measurement error, the universe could be flat, or it could be very slightly positively curved, closed, like a hypersphere, or very slightly negatively curved, open, hyperbolic. We simply cannot measure precisely enough yet to distinguish between these possibilities. If the universe is closed, if it curves back on itself as a three-sphere, then it exists as a three-dimensional surface in four-dimensional space. But this four-dimensional space is not something we can access or move through freely. It is a mathematical space that describes the embedding of our curved, three-dimensional universe, a conceptual framework for understanding how our space curves. We are confined to the three-dimensional surface, unable to step off it into the higher dimensional space around it, like being forever stuck on the surface of a sphere with no ability to jump off into the surrounding three-dimensional space. It is like how two-dimensional beings on the surface of a sphere are confined to that surface. They cannot leave it and float through the three-dimensional space around it. They are inherently stuck on the surface by the nature of their existence. For them, the surface is their entire reality, the totality of space. The three-dimensional space that the surface curves through is just a mathematical construct we use to describe how their surface curves, not a place they can visit or even conceive of visiting. It is beyond their dimensional access. Similarly, if our three-dimensional space is curved as a three-sphere, we are confined to it. The four-dimensional space is a mathematical construct describing the curvature, not a place we can visit or access. Or maybe it is a real physical space, and we truly are stuck on a three-dimensional surface within it, unable to perceive or move through the bulk four-dimensional space surrounding our three-dimensional surface. Perhaps there are physical laws that confine us to our three-dimensional surface, even though a larger four-dimensional space exists around us. This raises deep questions about the nature of dimensions, the structure of space, and the fundamental nature of physical existence. So what this concept means is profound and has deep implications for cosmology. It suggests that our three-dimensional world exists within a four-dimensional space. It is embedded in that higher dimension, wrapped up within it like a surface. And following the same logic, that four-dimensional world would exist within a fifth-dimensional space, and a fifth-dimensional world would exist within a sixth-dimensional world, and so on and so forth, continuing upward through higher and higher dimensions, each one curving within the next. If we take this idea seriously, if each spatial dimension exists as a curved surface within the next higher dimension, then we get a nested hierarchy. Lower dimensions embedded in higher dimensions, each curving through the space above it, each wrapped up within the next level. Our three-dimensional space is embedded in four-dimensional space. That four-dimensional space might itself be curved, existing as a four-dimensional surface within five-dimensional space. That five-dimensional space might be curved within six-dimensional space, and so on, potentially continuing upward forever, an infinite tower of dimensions, each containing the one below it, nesting like Russian dolls but in a way that transcends spatial metaphor. Each dimension would be slightly curved in the dimension above it, wrapping back on itself, existing as a surface within a higher dimensional space. This creates a nested structure, lower dimensions embedded in higher dimensions, each curving through the space above it, each level enabling the curvature of the level below. Now, I did mention earlier that nothing can be truly infinite, that infinity might not exist in physical reality. But if this theory of nested, curved dimensions is true, then I face a paradox, a fundamental problem with the theory. I am implying that a dimension is really contained within another dimension, which is contained within another dimension, which is contained within yet another dimension. This pattern continues upward in a never-ending sequence. And if it continues forever, then I am actually implying that there is an infinite amount of dimensions, an infinite hierarchy of spaces, each embedded in the next, with no top level, no final dimension. This is the only real problem I have with this theory of nested curved dimensions. It trades one infinity for another. Instead of each dimension being infinitely large, infinitely extended without bound, we now have infinitely many dimensions, a countably infinite sequence of higher and higher dimensional spaces. Does this progression ever stop? Is there a highest dimension, a top level beyond which the nesting does not continue, or does the nesting continue forever without end? If it continues forever, then infinity has sneaked back into our model, just in a different form, dressed in different clothes, appearing in a different guise. We have not eliminated infinity from our description of reality. We have just moved it from the extent of each dimension to the number of dimensions. Can infinite infinity really even be possible? Can we have an infinite tower of dimensions without logical contradiction or physical absurdity? Can infinitely many finite dimensions stack up coherently? We do not know the answer to that question definitively. It remains one of the deepest mysteries in theoretical physics and cosmology, one of the profound questions at the boundary of human knowledge, where mathematics meets physics meets philosophy. If physical infinities do not exist in our universe, if the universe must be finite in every way, including in the number of dimensions, then the nesting of dimensions must stop somewhere. There must be a highest dimension, a final level beyond which there are no more dimensions. Maybe the 10th dimension is the last. Maybe the 100th. Maybe the first dimension that contains itself in some strange self-referential topology that prevents further nesting, wrapping back on itself in a way that closes the sequence. We do not know. We have no empirical evidence to guide us. We can only speculate based on mathematical consistency, theoretical elegance, and philosophical preferences. Alternatively, maybe infinities do exist in nature. Maybe the tower of dimensions truly does go up forever, without end, without a top. Maybe there is no highest dimension, just as there is no largest number. The sequence continues infinitely. First dimension, second dimension, third, fourth, fifth, and so on, without limit. Each dimension is contained in the next, forever and ever, without end, turtles all the way up, dimensions all the way up. This is an open question in theoretical physics and cosmology. Different theoretical frameworks give different answers based on their assumptions and structures. String theory, for example, typically postulates a specific number of dimensions, often 10 or 11, depending on the version and the details of the compactification scheme. In these theories, there is a highest dimension. The dimensions do not nest infinitely. There is a stopping point, a final level. But string theory is unproven. It is an elegant mathematical framework with beautiful internal consistency, but we do not yet have experimental evidence that it correctly describes our universe. It may or may not be correct. Other theories are possible. Other approaches in theoretical physics allow for infinitely many dimensions in certain mathematical senses, though usually most of them do not play a significant role in physical processes or in the structure of observable reality. These extra dimensions might exist mathematically without having observable consequences. They might be inert, inactive, not participating in the dynamics of physics. We may never know the answer with complete certainty. These are questions at the absolute frontier of human knowledge, where observation ends and speculation begins, where measurement becomes impossible and we must rely on mathematical consistency and theoretical reasoning. They are questions where speculation and mathematics meet in attempts to understand the deepest structure of reality, the fundamental nature of space itself. What is clear is that the fourth dimension, whether it exists physically in our universe or only mathematically in our theories, is a logical extension of the dimensions we know. It follows patterns. It obeys rules. It is not arbitrary or magical. It is simply another direction in space, perpendicular to the three we experience, perpendicular to all of them simultaneously, in a way we cannot visualize but can understand logically. And even though we cannot visualize it, even though we can never point to it or move through it with our bodies, even though it remains forever beyond our direct perception and our visual imagination, we can understand it through mathematics. We can reason about its properties using logic. We can explore its implications through thought experiments. We can appreciate how it would change everything about space and geometry and perception if it were real, if it were accessible to us. This is the power of mathematics and logical reasoning. They extend our understanding beyond the limits of our senses. They allow us to think about realities we can never directly experience. They give us tools to explore possibilities that are invisible to us, that we cannot perceive with any sense organ, but that follow coherently from the patterns we observe in lower dimensions. The fourth dimension is not a mystical concept. It is not supernatural. It is not magic. It is not a metaphor for consciousness or enlightenment or any spiritual concept. It is a straightforward extrapolation of geometry into one more perpendicular direction. It is as natural an extension from 3 dimensions as 3 dimensions is from 2, or 2 dimensions from 1. It is the next step in a perfectly logical sequence. But it is an extension we cannot make physically, at least not in any way we currently understand. We cannot step into the fourth dimension. We cannot perceive it with our senses. We cannot even imagine it in any visual sense, cannot form a mental picture of it. It exists, if it exists, beyond the reach of our experience, accessible only through the abstract language of mathematics and logical reasoning. And that is both humbling and awe-inspiring. Humbling because it reminds us of the profound limits of human perception. We do not see reality as it truly is in its fullness. We see a limited projection, a simplified version that our brains can process using 2-dimensional images. We see 2-dimensional projections of a 3-dimensional world, and our brains infer the 3rd dimension using clever computational tricks. There may be aspects of reality all around us that we cannot detect because they exist in dimensions we do not have access to. Directions in space that we cannot point to or move through, perpendicular to all our familiar directions in ways we cannot visualize. But it is also awe-inspiring because it shows what the human mind can accomplish through pure reasoning. Without being able to see or touch or experience the 4th dimension directly, without any sensory access to it whatsoever, we can still understand it. We can describe it precisely using mathematical language. We can work with it rigorously using equations and logic. We can predict what it would be like if we could experience it. We can reason about its properties and implications. This is an extraordinary achievement of human thought, a testament to the power of abstract reasoning. So when we think about the 4th dimension, we should think about it as both a mathematical reality and a conceptual limit. It is real in the sense that mathematics describes it consistently and coherently, with no contradictions, no logical problems. It follows from patterns that are undeniable in lower dimensions, patterns we can observe and verify. It is a logical necessity if we continue the progression of dimensions according to the rules we understand. But it is also a limit to our perception. It represents something we can know about intellectually, but never truly experience directly. It is a reminder that reality may be far stranger and richer than what our senses reveal to us. There may be entire aspects of existence that are invisible to us, not because they are hidden by any physical barrier we could overcome, but because they exist in dimensions our minds are not equipped to perceive, our brains are not wired to process. This journey through dimensions, from the simple one-dimensional line to the mind-bending four-dimensional tesseract and beyond, reveals something profound about the nature of understanding itself. We can grasp concepts that we cannot visualize. We can reason about realities we cannot experience. We can extend patterns beyond the limits of our perception. We can understand things that are utterly alien to our direct experience. This is what makes us human in a deep sense. This is what separates us from other animals. This is what makes us capable of science and mathematics and philosophy, this ability to think about things beyond our immediate sensory experience, to reason about abstractions, to understand patterns that cannot be seen or touched. The fourth dimension exists, at least mathematically, as a completely coherent and well-defined concept. Whether it exists physically in our universe, whether our space has hidden extra dimensions, or whether 3 spatial dimensions plus time is all there is, remains an open question in physics. But either way, thinking about the fourth dimension expands our minds. It challenges our assumptions about what can be understood. It forces us to confront the limits of our perception and the extraordinary power of our reasoning. And that, in the end, is why the fourth dimension matters so deeply. Not because we will ever visit it, or see it, or use it practically in our daily lives, we almost certainly will not, but because it teaches us about the nature of space, the limits of perception, and the extraordinary power of the human mind to understand things that are utterly beyond our direct experience, things we can never see or touch, but can still comprehend through the magic of mathematical reasoning. The fourth dimension challenges us to think more clearly about what we mean by understanding. Can we understand something without visualizing it? Yes. Can we reason rigorously about something we cannot imagine? Yes. Can we discover truths about realities we cannot experience? Yes. Mathematics gives us this power. Logic gives us this capability. The fourth dimension is a testament to these tools, to our ability to extend our knowledge beyond the boundaries of our senses. This journey through the dimensions reveals the beautiful structure of space itself, the way each dimension builds on the previous one, following consistent rules and patterns. From the confined one-dimensional line, where a creature can only slide back and forth in a straight path forever, to the expansive two-dimensional plane, where movement gains a new degree of freedom and obstacles can be navigated around, to our familiar three-dimensional space, where we can build complex structures and contain things inside barriers, and finally to the four-dimensional space, which we can describe but never see. Each step follows a logical pattern. Each extension adds a perpendicular direction. Each new dimension is built from infinite copies of the dimension below. Understanding this progression, understanding how dimensions relate to each other, understanding why we perceive in one fewer dimension than we inhabit, all of this gives us a deeper appreciation for the structure of reality. It shows us that space is not just an empty container where things happen. Space has structure, it has properties, it has dimensionality, and these properties matter profoundly. They determine what is possible, what shapes can exist, how objects can interact, what kinds of movements are allowed, what can be enclosed and what cannot. Thank you for taking this journey through the dimensions with me. I hope you have gained not just an understanding of what the fourth dimension is, but an appreciation for why it is both impossible to visualize and perfectly possible to understand. The fourth dimension is a testament to the power of mathematical reasoning and the humility of recognizing that what we see is not all there is. There may be more to reality than our senses can ever reveal. aspects of existence that are forever hidden from our perception yet still comprehensible to our minds through logic and mathematics. The fourth dimension teaches us that understanding is not the same as visualization. We can understand things we cannot picture. We can reason about things we cannot experience. We can extend our knowledge into domains that our senses cannot access. This is the great power of human thought, the remarkable capability that allows us to explore not just the world around us, but worlds beyond our perception, realities we can never visit but can still comprehend through mathematics. As you rest and reflect on these ideas, consider the profound implications. Our everyday experience is just one thin slice of what might be possible. The three-dimensional world we navigate so confidently might be embedded in higher dimensions we cannot perceive. The barriers we rely on for privacy and security might be trivial to bypass from a higher dimensional perspective. The space we think we understand might curve back on itself in ways we cannot observe directly, wrapping around in dimensions beyond our access. And yet, despite these limitations, despite being trapped in 3 dimensions perceiving in 2, we can still understand the 4th dimension. We can reason about it. We can describe it. We can work with it mathematically. We can appreciate its structure and its implications. This is the extraordinary achievement of human thought. Understanding what we cannot see, knowing what we cannot experience, reasoning beyond the limits of our senses. Sweet dreams, and may your thoughts drift through dimensions both familiar and strange as you rest. May you appreciate the beauty of the mathematical patterns that govern space, the elegance of the progression from one dimension to the next, and the remarkable power of the human mind to understand realities beyond perception. The 4th dimension awaits in the realm of mathematical thought, forever beyond our sight, but never beyond our comprehension, a testament to the power of reason and the humility of accepting the limits of our senses. May you find wonder in the strange and beautiful structure of space itself, and in our ability to explore it through the power of logical thought.